In this section, we're covering 5.2, growth and decay. So we're going to use separation of variables to solve a simple differential equation. We'll get more into that in our next section. And then we're going to use exponential functions to model growth and decay. So this is a very common use of growth and decay in differential equations. So let's look at example 1, solving a differential equation. One of the things we want to do, or that we need to do, is we need to get the variables on the same side. So this is when we talk about separation of variables. We're saying get all your y's on one side and all of your x's on the other side. Okay. Now, um, one of the things that I like to do or like to think of is here we have our y prime, which we have used, but we've also used dy dx. And when I solve differential equations, I like to deal with dy dx because I have to get this x over on that side. At this point, here's my equation. I'm just going to cross multiply. So I'm going to go the y times dy equals 2x dx. Now, once you have your variables separated, you can integrate both sides. So I'm going to take the integral of y dy and then the integral of 2x dx. So this is y squared divided by 2 equals x squared plus c. Now, there is technically a plus c over there, but if I subtract c from both sides, I have another constant, and so we just combine them all into one c like we have done before. Um, so one of the things that the book will often do when we have our equations like this with multiple variables is you get the variables on one side and your constants on the other, and this is the general solution. Okay, so that's our general solution to our differential equation. So in many applications, the rate of change of variable y is proportional to the value of y. When y is a function of time, t, the proportion can be written as follows. So this is just, hey, here's our rate of change, and this is proportional. This is exponential growth and decay. So theorem 5.1, if y is a differentiable function of t, and y is greater than 0, and dy dt equals ky for some constant k, then this is the general solution. So we're just saying, hey, if you have y prime equals ky, then this will give you the general solution. Now, let's solve that, let's show that, and then we will see how this general solution came about, and then we'll talk about the different values. So to solve this, I'm going to write this as dy dx equals ky. So I'm going to pull the y, divide both sides by y, and multiply both sides by dx. So I'm going to take the integral of that. So I've got the natural log of y. Again, we talked about y is greater than 0. So I'll just drop those absolute values. The natural log of y equals kx. Okay. Now, I guess we have proportional to some time. So they use t instead of x. Now, before I forget, we have our plus c. So to solve this, I take e raised to both sides. So e natural log cancels, and I've just got y. Now this becomes the exponent. So this really is e to the kx times e to the c. C is just some constant, so e raised to c is just some other constant. And we put it in front. So y equals c e raised to the kx, and our equation up here says kt. So c is the initial value of y. And the reason that is true, if we put in 0 for t, this just has a value of 1. So when t is 0, c is our initial value. K is the proportionality constant. So exponential growth when k is greater than 0, and exponential decay occurs when k is less than 0. So we're going to see this as we go. Now, again, we could take this differential equation and solve it every time, like I just did, but this happens enough that we have a theorem so that we can shortcut that. All right, the rate of change of y is proportional to y. Okay, what that means is we can use this theorem. When t is 0, y equals 2. That's an initial value, so that tells me c is 2. When t is 2, y is 4. What is the value of y when t equals 3? So let's use this part here. So far I have y equals 2e to the k t. Now we need to find k, the value of k, our constant, proportionality constant. So what we do is we use our second set of values. So y is 4 when k times when t is 2. All right. So we solve this for k. Divide both sides by 2. So 2 equals e to the 2k. Now to get that variable outside of that exponent, I've got to take the natural log of both sides. So natural log of 2 equals 2k. So I'm going to divide by 2. And the natural log of 2 equals our k. So we can now write y equals 2e. Now when we do this, natural log of 2 divided by 2 is 0.3466. Oftentimes these proportionality constants will be given as a decimal. So that is our solution. Okay. Now it says, what is the value of y when t equals 3? We would just plug that into our calculator and go 2 times e to the 0.3466 times, what was our value, 3. And we would get approximately, y is approximately 5.657. Okay, radioactive decay is measured in terms of half-life, the number of years required for half of the atoms in a sample of radioactive material to decay. The rate of decay is proportional to the amount present. Proportional to the amount present, that means we can use our theorem from up above. I included these half-lives here, just it might be needed in some of these problems. So 10 grams of the plutonium isotope 239 were released in a nuclear accident. How long will it take for the 10 grams to decay to 1 gram? So y equals, what's our initial value? 10 e to the k t. All right, that's our general form. Okay, now I know that there will be 5 grams left after, see, plutonium, 24,100 years. Okay, so again, we're going to solve this. 1/2 equals e to the 24,100k. So we'll take the natural log of both sides. Natural log of 1/2 equals 24,100k. Divide by the 24,100. And that gives us k equal to approximately negative 0.000286761. Make sure I have the right number of zeros. Yep, that looks good. So this is modeled y equals 10 e to the negative 0.000286761 t. So now it asks us to solve for 1 gram. So when will there be 1 gram left? So we substitute in 1, and we're going to solve for t. So I'm going to divide by 10, and I get 1/10 equals e raised to that exponent. So I need to take the natural log of both sides. Natural log of 1/10 equals negative 0.000028761t. So I'm going to divide by the negative decimal. And we get approximately time equals 80,059 years. Population growth, example 4. An experimental population of fruit flies increases according to the law of exponential growth. There were 100 flies after the second day of the experiment and 300 after the fourth day. Approximately how many flies were in the original population? So what we're going to do is we're going to look at 100 flies equals our initial population, which we don't know, times e to the k times 2. So second day, 100 flies. And then 300 flies, c e to the k times 4 on the fourth day. So we have an equation, two equations with two unknowns. So we can solve for our unknowns, which is our initial population. And we could also solve for the proportionality constant. So what I'm going to do is I'm going to divide by e to the k2 here to figure out what c is, or at least an expression for c. Now, instead of dividing by k2, e to the k2, I'm going to go 100 times e to the negative, we'll call it 2k power. So that means 300 equals, now we're substituting in our value for c, 100 e to the negative 2k times e to the 4k. So I'm going to divide by 100 here. So 3 equals e to the 2k. We combine these exponents by adding them. So take the natural log of both sides. So natural log of 3 divided by 2 will equal k. I also divided by 2 there. And that is approximately 0.5493. So our equation is some constant c times e to the 0.5493 t. We need to find the c now, so I'm going to substitute in the values. We'll do 100 after 2 days. So I'll do 100 divided by e to the 0.5493 times 2. And our c is approximately 33. We're dealing with fruit flies. Half of a fruit fly wouldn't count as part of the population. So we'll go to approximately 33. And that answers our question. We could go back and rewrite our equation. There's the equation that represents this fruit fly population growth. Okay, example 5. 4 months after it stops advertising, a manufacturing company noticed that its sales have dropped from 100,000 units per month to 80,000 units per month. The sales follow an exponential pattern of decline. What will the sales be after another 2 months? So our 100,000 should be our initial value. So we don't have to write two equations this time and solve the system. We're just going to write one equation. Our initial value, our initial sales is 100,000, and that's e to the kt. Sorry, we are plugging in our value of t here. So this is 4 months. So there's our t value, 4. So we divide by the 100,000. Cancel that side, and we get 8 equals e to the 4k. So again, take the natural log. We'll divide by 4. I hope you see that these steps are happening. So k equals natural log of 8 divided by 4 is approximately negative 0.0558. Okay, so after another 2 months, y equals 100,000 e to the negative 0.0558 t. What we'll do is we'll put 6 in here for t, because 2 more months after the 4 months. Put that into the calculator, and that's approximately 71,500 units. Newton's law of cooling. Let y represent the temperature in degrees Fahrenheit of an object in a room whose temperature is kept at a constant 60 degrees. The object cools from 100 to 90 in 10 minutes. How much longer will it take for the temperature of the object to decrease to 80 degrees Fahrenheit? Now this may seem very similar to the previous one, but there's a couple extra steps that we have to do. Newton's law of cooling tells us that the rate of change in y is proportional to the difference between y and 60. Okay, and that just makes sense. If I put an object that's 100 degrees Fahrenheit in a room that was 90 degrees, it would cool less quickly than if I put it in a room that was 0 degrees. And so this rate of change, this change in temperature, varies depending on the difference between the two temperatures. So the rate of change in y is proportional to the difference between the temperature, the object, and the temperature in the room. Okay, so this is where we start. Let's solve this. We're not going to put our values in. I need to separate my variables. So I've got dy over y minus 60 equals k dt. We'll integrate both sides. So this gives me the natural log of y minus 60 equals kt plus c. Now, because we start with a value above 60 degrees, this is going to be a positive, so we're going to drop these absolute values. Now, using exponential, we're going to raise both sides to e. That's going to give us y minus 60 equals c e to the kt. Similar to what we did when we proved this theorem. And then we add 60 to both sides. So y equals 60 plus c e to the kt. Now this is our formula. So when we have 100, we know 100 to 90 in 10 minutes. Before we do that, we've got to figure out c. When time was 0, y was 100. So 100 equals 60 plus c e to the kt will go up to 1. That means c is 40. That's the difference between the temperatures. So now we have another piece of our equation. Y equals 60 plus 40 times e to the kt. So now we need to find out our k, our proportionality constant. And to do that, we'll use the 90 and the 10. So 90 equals 60 plus 40 e to the k times 10. So subtract 60, and then we'll divide by 40. That's 3/4 equals e to the 10k. Natural log of both sides, divide the 10k. So natural log, the e cancels. natural log of 3/4 divided by 10 is approximately negative 0.02877. So we type that into our calculator. So now we have our full equation. Y equals 60 plus 40 e to the negative 0.02877 t. We can go back and actually answer the question, how much longer will it take for the temperature of the object to decrease to 80 degrees Fahrenheit? So I'm going to put my 80 equals, we'll subtract 60, divide by 40 again. So that gives me 1/2 equals e to the negative 0.02877 t. Natural log both sides. Divide by our proportionality constant. So natural log of 1/2 divided by our proportionality constant is 24.09 minutes, is approximately t. And so approximately 14.09, which is about 5 seconds, I think, minutes, because it said how many more minutes will it take. And there are some examples of exponential growth and decay and differential equations to assist us in that. Thank you for watching.